In this lecture, I will answer two questions. In the first question, we find out the area of this green shape that is inside square TSQP, and in the second question, we find out the area of this green shape that is inside square ADCB. So we start with the first question. In the drawing, we have two squares. We have the big square TSQP and we have the small square ABCP. In addition, we have quadrilateral MBCP. This is equal to 27 square inches inside. This is triangle AMP. This is equal to 9 square inches inside. Again, our task is to find out the area of this green shape. So first of all, it is very easy to see. It's very easy to find the area of this small square ABCP. The area of the small square ABCP will be equal to the area of quadrilateral MBCP, that is 27, plus the area of this triangle AMP, that is 9. So in total, the area of the small square ABCP will be equal to 27 plus 9, that is 36. So the area of the small square ABCP is equal to 36 square inches inside, that is from one side, but from the other side, we know that the area of any square equals to the length of one side squared. Therefore, the area of this small square ABCP will be equal to the length of side AP squared. That is to say, it is equal to AP squared. So from the other side, the area of square ABCP is equal to AP squared. And from this equation, AP squared equals to the area of square ABCP equals to 36. We will derive that AP squared equals to 36. Here we take out all this equation and finally we get that AP equals to the square root of 36, that is 6. So AP equals to 6 units in there. This is side AP is equal to 6 units in there. We know that all the angles inside in the square are right angles. So in the small square ABCP, this is a right angle. And therefore, triangle AMP is a right angle. It is given us the question that the area of the right triangle AMP is equal to 9 square inches in size from one side, but from the other side, we know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this right triangle AMP will be equal to the base AM times the height AP over 2. So as you know, we found out that the area of the right triangle AMP from one side it is equal to 9 square inches in size according to what is given as the question. But from the other side we know that the area of the right triangle AMP equals to the base AM times the height AP over 2. Again, the area of the right triangle AMP from one side is equals to 9 square inches inside, from the other side is equals to the base AM times the height AP over 2. From this equation, AM times AP over 2 equals to the area of the right triangle AMP equals to 9. We will derive that AM times AP over 2 is equal to 9. We only found out that AP equals to 6, so we solve AP by 6. And we get that AM times 6 over 2 equals to 9. 6 over 2 is 3. So total this of the equation we have 3 AM is equal to 9. Here we divide this equation by 3 and finally we get that the missing side AM is equal to 9 over 3, that is 3. This is the missing side AM. Is equal to 3 units in its length. In the next step, I'll copy the right triangle AMP in a new page and we'll implement on this right triangle AMP the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. This is the right triangle AMP that according to the original law and according to the Pythagoras theorem. In this right triangle AMP, MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. So I'll write it down. MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so we'll leave it as it is. So it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9, plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So in total, we should find out that MP squared equals to 9 plus 36, that is 45. MP squared equals to 45. Here we will substitute MP by 9 times 5 and get that MP squared equals to 9 times 5. Here we take a root out of the equation and finally get that MP equals to the square root of 9, that is 3, so inside the root we left only 5. So in total MP equals to 3 times square root of 5 units in its there. Therefore MP equals to 3 times square root of 5 units in its there. This is side MP is equals to 3 times square root of 5 units in its there. you know that all the angles inside the square are right angles. So in the big square TSQP, this is the right angle. What is the length of this missing line segment? Line segment MB. From the drawing, it is very easy to see that MB in total equals to AB minus AM. So MB equals to AB minus AM. We know that all the sides of a very square are equal to each other. AP equals to 6, therefore AB must be also equal to 6. So AB is 6 minus AM. AM is 3, so MB total equals to 6 minus 3, this is 3. If you found out that line segment MB, the missing line segment MB equals to 3 units in its length. We know that those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in the big right angle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this part of this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, the small right angle TMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right triangles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, then therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the angles of the big right triangle A and P was only equal to all the angles of this small right triangle T and B, therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. If you found out that the big right triangle A and P is similar, this is the sign of similar to the small right triangle TMB according to angle similarity rule. And then again, if you found out that the right big triangle A and P is similar to the small triangle T and B according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AP of the big right triangle A and P over side TB of the small right triangle T and B is equal to side AM is equal to side AM of the big right triangle A and P over side TM of the small right triangle TMB, and it is also equals to side AMP of the big right triangle AMP over side AMB of the small right triangle TMB. And again, from the fact that those two right triangles are similar to each other, we would have that the following relationship exists between their sides. We would have that side AMP of the big right triangle AMP over side TB of the small right triangle TMB is equal to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equal to side AMP of the big right triangle AMP over side AMB of the small right triangle TMB. AP equals to 6 over TB. TB is the missing side, so we have this it is. And it is equal to AM. AM is 3 over TM. TM is the missing side, so we have this it is. And it is also equal to side MP. This is 3 times square root of 5 over side MV, this is equal to 3. Simple that, we should find out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator and 3 in the denominator, so 3 get cancelled, we left only with square root of 5. So we should find out in total that 6 over TB equals to the square root of 5, and it is also equal to 3 over TM. And again, I should find out that 6 over TB equals to the square root of 5, and it is also equal to 3 over TM. Those two sides are equal to each other. That is to say 6 over TB equals to the square root of 5. Here we multiply this equation by TB and then we divide it by square root of 5, and we get that TB is equal to 6 over square root of 5 units in its term. This is the missing side TB. This is equal to 6 over square root of 5 units in its term. Those two sides are also equal to each other. That is to say, square root of 5 equals to 3 over 2 TM. Again, square root of 5 equals to 3 over TM. Here we multiply this equation by TM and then we divide it by square root of 5, and in total we get that TM is equal to 3 over square root of 5 units in its term. This is the missing side of TM. This is equals to 3 over square root of 5 units in its term. In the next step, we find out the left of side TP of the big square TSQP. TP in total equals to TM plus MP. So that you know, TP equals to TM plus MP. And again, one side of this big square TSQP, TP, is equal to TM plus MP. So TP in total equals to TM. TM is 3 over square root of 5 plus MP. MP equals to 3 times square root of 5. So in total we know that TP equals to 3 over square root of 5 plus 3 times square root of 5. So TP equals to 3 over square root of 5. Here we'll multiply 3 times square root of 5 by square root of 5, and then we divide by square root of 5 in order to have a common factor with this number. And we get that square root of 5 times square root of 5 is 5, and 5 times 3 is 15. So in total, the number of this expression we have 15. And we have to divide it by square root of 5. So in total, we know that TP equals to 3 plus 15 over square root of 5. 3 plus 15 is 18, so TP in total equals to 18 over square root of 5 units in its length. This is side TP, that is equals to 18 over square root of 5 units in its length. TP equals to 18 over square root of 5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape in total equals to the area of the big square TSQP minus the area of this quadrangle MBCP minus the area of this right triangle TMB. Repeat again, the area of this green shape in total equals to the area of the big square TSQP minus the area of this quadrangle MBCP minus the area of this right triangle TMB. So write it down. I should found out that the area of the green shape in total, it is equal to the area of the big square TSQP minus the area of this quadrangle MBCP is equal to 27 square meters in its size. Minus the area of this right small triangle TMB. So repeat again, we found out that the area of this green shape in total it is equal to the area of the big square TSQP minus the area of quadrangle MBCP minus the area of the small right triangle TMB. What is the area of the big square TSQP? We know that the area of any square equals to the length of one side squared. Therefore, the area of this big square TSQP will be equal to the length of side TP squared. This is to say it is TP squared. And again, the area of the big square TSQP equals to TP squared minus the area of quadrangle MBCP. It's given us the equation that the area of this quadrangle MBCP is equal to 27 square meters in size. So it is minus 27 minus the area of the small right triangle TMB. We know that the area of any triangle equals to the base of the triangle times the height of the base over 2. Therefore, the area of this triangle TMB will be equal to the base TB times the height TM over 2. Now that triangle TMB equals to the base TB times the height TM over 2. So the area of the big square equals to TP squared. TP is 18 over square root of 5. And therefore, TP squared will be equal to 18 over square root of 5 squared. TP squared equals to 18 over square root of 5 squared. Minus the area of quadrilateral MBCVD is 37. Minus the area of the small right triangle TMB is equal to TB times TM over 2. The base TB is 6 over square root of 5 times the height TM, that is 3 over square root of 5, divided by 2. So now we should know that the area of the small right triangle TMB equals to the base, that is 6 over square root of 5 times the height, that is 3 over square root of 5, divided by 2. The area of the big square TSQP equals to 18 over square root of 5 squared. 18 over square root of 5 squared equals to 18 squared, that is 324, over square root of 5 squared, that is 5. So now if you want to know that the area of the big square equals to 324 over 5 minus 27, and here we have the area of the small right triangle TMB equals to 6 times 3 is 18, so in total in the numerator we have 18 divided by square root of 5 times square root of 5 is 5, and 5 times 2 is 10. (324 over 5 is 64.8). Minus 27 minus 18 over 10. 18 over 10 is 1.8, so it is minus 1.8. 64.8 minus 1.8 is 63 minus 27. 63 minus 27 is 36. So total, if you want to know that the area that we are looking for this question, that is the area of this green shape, is equal to 36 square inches in size. So written down, if you want to know that the area of the green shape in total is equal to 36 square inches in size. And that is the answer to the first question. Repeat again. The area of this green shape is equal to 36 square inches in size. So we finish with the first question. In the next step, I will present you the second question, and so the second question of this lecture. The second question, our task is to find out the area of this green shape. So in the drawing we have square ABCD. We know that one side of square ABCD equals to 10, and therefore all the other sides, AB, BC, CD, and DA, must be also equal to 10. In addition, inside this square ABCD we have this quarter circle. The center of this quarter circle is 0 at point A. Point A is the center of the quarter circle. Point B is the point of the quarter circle itself. Therefore, AB is the radius of the quarter circle. Is equal to 10. Likewise, AD is also the radius of the quarter circle. Is equal to 10. In addition, inside this big square BCD, we have this semicircle. The diameter BC of the semicircle equals to 10. We define the center of this semicircle. This point is point O. If the diameter of the semicircle is 10, then the radius must be equal to half of it. That is to say, the radius must be equal to 10 over 2, that is 5. So the radius OB of the semicircle equals to 5. And the radius OC of the semicircle equals to 5. In the next step, we will define the intersection point between this semicircle and this quarter circle. This point is point M. And we'll join points O and M together by straight line. Point O is the center of the semicircle. Point M is the point of the semicircle itself. Therefore, OM is the radius of the semicircle. This is equal to 5 units in its length. In the next step, we'll join points A and M together by straight line. Point A is the center of the quarter circle. Point M is the point of the quarter circle itself. Therefore, AM is the radius of the quarter circle. That is equal to 10 units in its length. What is the definition of line segment AM? Line segment AM is tangent to the semicircle at this point, point M. Therefore, line segment AM is a tangent. So, here we can implement rule 1 in our drawing. Why? Because we have the radius OM of the semicircle that is equal to 5. The radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever we have radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees according to rule 1. We know that all the angles inside any square are right angles. Therefore, in square ABCD, this is the right angle. In the next step, we will join points A and O together by a straight line. By joining points A and O, we created those two right angles. This is the right angle ABO and this is the right angle AMO. In the next step, we'll prove that those two right angles can go into each other according to side rule. So now we have to prove that the right angle ABO can go into the right angle AOM according to side rule. So why those two right angles can go into each other? First of all, side OB of the right angle ABO equals to side OM of the right angle AOM. They are both the radii of the semicircle is equals to 5 and therefore they are equal to each other. So quindi again, je prends that OB equals to OM equals to 5. In addition, side AB of the right triangle ABO equals to side AM of the right triangle AOM. The above the area of the quarter circle that is equals to 10, and therefore they are equal to each other. Again, side AB of the right triangle ABO equals to side AM of the right triangle AOM. The above the area of the quarter circle is equal to 10, and therefore they are equal to each other. And finally, AO is a common side that belongs to both triangles, so you can write down that AO equals to itself is a common side that belongs to both triangles. And again, AO is a common side that belongs to both triangles, so AO equals to itself is a common side that belongs to both triangles. So if you prove that all the three sides of this right triangle ABO correspond equal to all the three sides of this right triangle AOM, and therefore those two right triangles can go into each other according to side rule. So write it down. Repeat again, let's remember that the right triangle ABO congruent, this is the sign of congruent to the right triangle AOM. According to side rule. And from the fact that those two right triangles can go into each other, we will derive those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their sizes. So if we find the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Likewise, from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. We know that the sum of the before that we will focus on the right triangle ABO and we implement the Pythagoras theorem on this right triangle ABO. So I copy the right triangle ABO in a new page and we will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the pressure of whatever solid. So actually, this is the right line ABO that I go from the original drawing. This right line ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So write it down. AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so leave it as it is. So it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total we should know that AO squared equals to 100 plus 25, that is 125. So AO squared equals to 125. Here we substitute 125 by 25 times 5 and get that AO squared equals to 25 times 5. Here we take a root out of this equation and finally we get that the missing hypotenuse AO is equal to the square root of 25, that is 5, so inside the root we left only with 5. So in total we should know that AO equals to 5 times square root of 5 units in its length. This is the hypotenuse AO, that is equals to 5 times square root of 5 units in its length. We will continue to focus on this right line ABO. In the right line ABO, sinus alpha equals to BO over AO. Again, in the right line ABO, sinus alpha equals to BO over AO. So sinus alpha equals to BO, here, sinus alpha equals to BO is 5 over AO equals to 5 times square root of 5. So in total, if you want to know that sinus alpha equals to 5 over 5 times square root of 5. Sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled, and we left only with 1 over square root of 5. So in total, we will know that sinus alpha equals to 1 over square root of 5. Our task is to find out the value of angle alpha itself, the size of angle alpha. In order to find out the size of angle alpha, we will operate the opposite function of sine, that is arc sine, on the result of sinus alpha, that is 1 over square root of 5, This way we'll get the value of angle alpha itself. So arc sine that is the opposite function of sine of 1 over square root of 5 is equal to angle alpha itself, the size of angle alpha. And we know that arc sine of 1 over square root of 5 is equal to 26.565 degrees in its size, and it is equal to alpha. So if you found out that the size of angle alpha is equal to 26.565 degrees in its size, and therefore 2 alpha must be equal to 2 times 26.565, that is actually 53.13 degrees. Angle MAB, this is angle MAB, that equals to 2 alpha, alpha plus alpha is 2 alpha. So angle MAB equals to 53.13 degrees in its size. We will continue to focus on the right triangle ABO. This is the right triangle ABO. In this right triangle ABO, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle ABO? We have angle alpha plus beta plus 90 degrees, in total must be equal to 180 degrees. So if we go in the right triangle ABO, alpha plus beta plus 90 degrees, in total the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we will subtract 90 degrees from this equation, and finally we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we will subtract alpha from this equation, and finally we get that beta equals to 90 degrees minus alpha. Beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha. We found out, okay, that the size of angle alpha is 26.565 degrees. So alpha is 26.565 degrees. And beta equals to 90 degrees minus 26.565, this is actually equal to 63.435 degrees in size. Angle beta equals to 63.345 degrees in its size. And therefore 2 beta equals to 63.345 degrees times 2, that is equal to 126.87 degrees in its size. This is angle MOB. Angle MOB equals to beta plus beta, that is 2 beta. We just found out that 2 beta equals to 126.87 degrees in size. So angle 2 beta is equal to 126.87 degrees in its size. our task is to find out the area of this green shape. In order to find out the area of this green shape, we will join points M and B together by straight line. By joining points M and B, we divided the green shape into two parts. This is the first part and this is the second part. The first part is a segment. So we define this upper segment as segment MUB. And again, this is the upper segment MUB. And the second part is this segment. This is the lower segment. So we define the lower segment as segment MLB. And it is very clear that the area of the green shape in total equals to the area of the upper segment PUM plus the area of the lower segment MLB. So we calculate the area of each segment separately, and then we net the two areas with each other, and this will be the area of this green shape. That is the area that we are looking for in this question. So first of all, we calculate the area of the lower segment MLB. In order to find out the area of the lower segment MLB, I'll copy sector ABM in the page, and we run this sector ABM. So, first of all, what is a sector? A sector is a portion of a circle enclosed by two radii in the arc between them. Repeat again on the definition of a sector. The green shape AOB is a sector, the sector AOB. So a sector is a portion of a circle. You can say that this sector is a portion of this circle enclosed by two radii and the arc AB between those two radii. The two radii are defined as the legs of the sector. Now, the area of the circle, of course, and the area of this sector AOB equals to pi r squared. That is the area of the circle that contains the sector. R is the radius of the circle, of course, times the angle between the legs of the circle, that is theta, over 360 degrees. And again, the area of this sector AOB equals to pi r squared times theta over 360 degrees. So repeat again that a sector is a portion of a circle enclosed by two radii and arc AB between them, and the area of a sector equals to pi r squared times theta over 360 degrees. This is sector ABN, that according to the original drawing, the rounded side above A and B is assigned for a sector. This is sector A and B. the angle between the legs of the circle is this angle A and B. Angle A and B equals to 2 alpha, and we already found out that 2 alpha equals to 53.13 degrees in its size. So the angles between the legs of the circle is equal to 53.13 degrees. And the legs of the circle are actually the two radii of the quarter circle. AB is 10, AM is also 10. Now the two radii of the quarter circle is equals to 10. AB equals to 10, AM also equals to 10. So according to the formula that I presented to you a couple minutes ago, the area of this sector A and B will be equal to the area of the circle that contains the sector, that is actually pi r squared. R equals to 10 times the angle between the legs of the circle, that is 53.13 degrees, divided by 360 degrees. R is 10, therefore R squared is 10 squared, that is 100, so pi r squared is 100 pi, times 53.13 degrees over 360 degrees. The value of this expression in total, this is to say the value of 100 pi times 53.13 degrees over 360 degrees, in total it is equal to 46.3646 coordinates in size. So if you want to know that the area of this sector A and B, in total it is equal to 46.3646 coordinates in size. Our task is to find out the area of this lower segment BLM. This is the lower segment BLM. This is the lower segment BLM that we have to find out the area of this lower segment. Lower segment BLM. So what is the area of this lower segment BLM? This is the lower segment BLM. So what is the area of this lower segment BLM? From the drawing, it is very easy to see that if you remove from this sector A and B this triangle A and B, we get exactly this segment BLM. But again, if you remove from this sector A and B this triangle A and B, we get exactly sector B. We get exactly segment BLM. And therefore, the area of segment BLM will be equal to the area of sector BLM minus the area of triangle ABM. So write it down. In total, we should know that the area of the lower segment BLM equals to the area of sector ABM this is sector ABM. This is sector ABM. Minus the area of this triangle ABM. if you remove from this sector ABM, triangle ABM, we get exactly the lower segment BLM. And therefore, the area of the lower segment BLM equals to the area of sector ABM minus the area of triangle ABM. Angle BAM equals to 53.13 degrees, AB equals to 10, AM also equals to 10. We already found out that the area of this sector ABM is equal to 46.3646 coordinates in size minus the area of this triangle ABM. In order to find out the area of this triangle ABM, I will present to you a new formula that will help us to find out the area of any triangle. This is triangle ABC, that's called Venn triangle. This triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. According to this formula, the area of any triangle equals to A times B times sinus theta over 2. Okay, again, the area of this triangle ABC that's called Venn triangle equals to the multiplication of two sides by each other, that is to say A times B, times sinus angle between those two sides, that is theta. So it is times sinus theta over 2. So the area of the side ABC is equal to A times B times sinus theta over 2. We use the new formula in order to find out the area of this triangle times ABM. According to the formula that I presented to you, the area of this triangle ABM will be equal to AB times AM, that is the multiplication of two sides by each other, times sinus the angle between those two sides, that is 53.13 degrees over 2. And again, the area of this triangle ABM equals to AB times AM times sinus 53.13 degrees over 2. AB is 10, AM is also 10, and sinus 53.13 degrees is equal to 0.8 divided by 2. 10 times 10 is 100, and 100, we have 100 times 0.8 over 2. 100 over 2 is 50, and 50 times 0.8 is 40. So total we found out that the area of this triangle ABM equals to 40 square units in its size. And the area of this lower segment BLM is equal to the area of sector ABM, that is 46.364 square units in its size, minus the area of this triangle ABM, that equals to 40 square units in its size. So 46.3646 minus 40 is equal to 6.3646 square units in its size. So in total we found out that the area of this lower segment BLM is equal to 6.3646 square units in its size. So this is the lower segment BLM, that is equal to 6.3646 square units in its size. In the next step we find out the area of this upper segment BUM. In order to find out the area of this upper segment BUM, I will copy sector BOM in a new page and analyze this sector BOM. So actually, this is sector BOM, the current under drawing. The angle between the legs of this sector is angle BOM. And remember this also that angle BOM is equal to 2 beta, and 2 beta equals to 126.87 degrees in its size. Angle BOM equals to 126.87 degrees in its size. The legs of the sector OB and OM are the radii of the semicircle, is equals to 5. BO equals to 5 and OM also equals to 5. According to the formula that I presented to you, the area of this sector must be equal to pi r squared. This is the area of the circle that contains the sector. The radius of the circle is 5. Times the angle between the legs of the sector, that is 126.87 degrees, divided by 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi, times 126.87 degrees over 360 degrees. Actually, in total, the value of this expression, 25 pi times 126.87 degrees over 360 degrees, in total is equal to 27.678 square in its size. So if you found out that the area of this sector BOM is equal to 27.678 square in its size. Our task is to find out the area of this upper segment BOM. We have to find out the area of this upper segment BOM. So what is the area of the upper segment BUM? This is the upper segment BUM. This is the upper segment BUM that we have to find out the area of this segment. From the drawing, it is very easy to see that if you remove from this sector OBM, this side OBM, we get exactly segment BUM. And therefore, the area of segment BUM will be equal to the area of sector BOM minus the area of side BOM. Writing down the area of the upper segment BOM in total is equal to the area of sector BOM minus the area of this target BOM. And again, from the drawing, it is very easy to see that if you remove from this sector BOM, triangle BOM, we get exactly segment BUM. And therefore, the area of segment BUM equals to the area of sector BOM minus the area of triangle BOM. We already found out that the area of this sector BOM equals to 27.678 square in size. minus the area of this triangle BOM. Angle BOM equals to 126.87 degrees in its side. BO equals to OM equals to 5. They are both the radii of the semicircle is equals to 5. According to the formula that I presented to you, the area of this triangle BOM will be equal to BO times OM, that is the multiplication of two sides by each other, times the angle between those two sides, that is times sinus angle between those two sides, that is actually sinus 126.87 degrees divided by 2. BO is 5, OM is also 5, so it is 5 times 5 times sinus 126.87 degrees. Sinus 126.87 degrees is equal to 0.8 divided by 2. 5 times 5 is 25, and 25 over 2 times 0.8 is the area of this triangle BOM. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So in total we found out that the area of this triangle BOM equals to 10 square inches in size. And therefore, the area of this lower segment BUM will be equal to the area of sector BOM, that is 27.678 square inches in size, minus the area of this triangle BOM, that is 10 square inches. 27.678 minus 10 is 17.678. And again, if you found out that the area of this upper segment BUM is equal to 17.678 square inches in size. So actually, this is the upper segment BUM, and we just right now found out that the area of this upper segment BUM is equal to 17.678 square inches in size. Our task is to find out the area of this green shape. It is very clear that the area of this green shape equals to the area of the upper segment BUM, that is 17.678 square inches in size, plus the area of the lower segment BLM, that is equal to 6.3646 square inches in size. So in the now we found out that the area of the green shape in total is equal to the area of the upper segment BOM plus the area of the lower segment BLM. We already found out that the area of the upper segment BOM is equal to 17.678 square inches in size, plus the area of this lower segment BLM is equal to 6.3646 square inches in size. So in total, the area of this green shape is equal to the area of the upper segment BUM, that is equal to 17.678, plus the area of this lower segment BLM, that is equal to 6.3646 square inches in size. So write it down. If you found out that the area of the green shape, that is the area that you are looking for in this question, is equal to the area of the upper segment BUM, that is equal to 17.678 square inches in size, plus the area of the lower segment BLM, that is equal to 673646 square inches in size. And 17.678 plus 6.3646 in total is equal to 24.02426 square units in size. And again, we should find out that the area of this green shape, that is the area that we are looking for in this equation, it is equal to 24.0426 square units in size. The area of this green shape, in total it is equal to 24.0426 square units in size. So we finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our task in the first question was to find out the area of this green shape. So in the drawing we have two squares. This is the big square TSQP and this is the small square ABCP. In addition, we have also this quadrilateral MBCP that is equal to 27 square units in size according to what is given as the equation. And we have also this triangle AMP that is equal to 9 square units in size. Again, our task is to find out the area of this green shape. So first of all, it is very easy to say that the area of the small square ABCP is equal to the area of quadrilateral MBCP, that is 27 square units, plus the area of this triangle AMP is equal to 9 square units in size. And therefore, in total, the area of this square ABCP will be equal to 27 plus 9, that is 36 square units in size. So from one side, the area of the small square ABCP is equal to 36 square units in size, but from the other side, we know that the area of any square equals to the length of one side squared. And therefore, the area of this square ABCP will be equal to the length of side AP squared. That is to say, it is AP squared. So from the other side, the area of the small square ABCP will be equal to AP squared. From one side it is equal to 36 units in size. From one side it is equal to 36 units in size, and from the other side it is equal to AP squared. And from this equation, AP squared equals to the area of square ABCP equals to 36. We derive that AP squared equals to 36. Here we took out of this equation and found out that AP equals to the square root of 36, that is 6. This is side AP, this is equal to 6 units in its length. We know that the angles inside, all the angles inside the square are right angles. So in square ABCP, this is the right angle, and therefore triangle AMP is a right angle. Okay? We know that the area of this right triangle AMP is equal to 9 square units according to what is given as the equation from one side, but from the other side we know that the area of the triangle equals to the base of the triangle times the height over 2. And therefore, the area of this triangle AMP will be equal to the base AM times the height AP over 2. So if again, if you know that from one side, according to what is given as the equation, the area of the right triangle AMP is equal to 9 square units in its size. But from the other side, the area of the right triangle AMP is equal to the base AM times the height AP over 2. From this equation, AM times AP over 2 equals to the area of the right triangle AP equals to 9. We derive that AM times AP over 2 equals to 9. So AM times AP over 2 equals to 9. AP is 6, so AP by 6, and found out that AM times 6 over 2 equals to 9. 6 over 2 is 3, so in total on this side of the equation we have 3 times AM equals to 9. Here we divided this equation by 3, and found out that the length of the lines, the missing line segment AM is equal to 3 units. This is the missing line segment AM is equal to 3 units in its length. In the next step, I copied the right triangle AMP in a new page and we implemented the Pythagoras theorem on this right triangle AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is right triangle AMP that I copied from the original drawing. according to the Pythagoras theorem, in this right triangle MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so if this it is. So it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3, that is 9, plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So total MP squared equals to 9 plus 36, that is 45. MP squared equals to 45. Here we substituted 45 by 9 times 5, and therefore we have MP squared equals to 9 times 5. Here we took out of this equation and finally found out that MP, the length of the hypotenuse MP, is equals to the square root of 9, that is 3, so inside the root we left only 5. So in total MP equals to 3 times square root of 5 units in its length. This is side MP, this is equals to 3 times square root of 5 units in its length. What is the length of this missing 9 segment MB? From the drawing, it is very easy to see that MB in total equals to AB minus AM. Again, MB equals to AB minus AM. We know that all the sides of square ABCP are equal to each other. AP equals to 6, therefore AB must be also equal to 6. So MB equals to AB, that is 6, minus AM, that is 3. So total MB equals to 6 minus 3, that is 3. This is the missing side MB, this is equals to 3 units in its length. We also know that all the angles inside in the square are right angles. So in the big square DSQP, this is a right angle. We also know that those two angles are defined as vertex angles, so you know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in a triangle. Likewise, in the small right triangle TMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the figures on the right triangle AMP are correspondingly equal to the figures of this right triangle TMP, and therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again. If you want to know that the right triangle AMP is similar, this is the sum similar to the right small triangle TMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right triangle AMP of the big right triangle AMP or side TB of the small right triangle TMB is equal to side AM of the right big triangle AMP over side TM of the right small triangle TMB, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TMB. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right triangle AMP over side TB of the smaller right triangle TMB is equal to side AM of the right triangle AMP over side TM of the right triangle TMB, and it is also equal to side MP of the right triangle AMP over side TB of the right triangle TMB. AP equals to 6 over TB. TB is the missing side of limited cities, and it is equal to AM. AM is 3 over TM. TM is the missing side of limited cities, and it is equal to MP. MP is 3 times square root of 5 over MB. MB is 3. So in total, we should find out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. We have 3 in the numerator, 3 in the denominator, so 3 will get cancelled. We left only square root of 5 here. So in total, we should find out that 6 over TB equals to the square root of 5. equals to 3 over Tm. Those two sides are equal to each other. So we get the first equation from those two sides. This is to say 6 over Tb equals to the square root of 5. 6 over Tb equals to the square root of 5. Here we multiply this equation by Tb and then we divide it by square root of 5 and finally found out that Tb equals to 6 over the square root of 5 units in its length. Likewise, those two sides are also equal to each other, so this is again the equation from those two sides. That is to say, square root of 5 equals to 3 over Tm. Here, square root of 5 equals to 3 over Tm. Here we multiply this equation by Tm and then we divide it by square root of 5 and finally found out that Tm equals to 3 over square root of 5 units in its length. This is the missing side Tm, this equals to 3 over square root of 5 units in its length, and we already found out that Tb equals to 6 over square root of 5 units in its length. In the next step, we found out the length of side Tp of the big square TSQP. Tp equals to Tm plus Mp. Okay, again. Tp equals to Tm plus Mp. So Tp equals to Tm. Tm is 3 over square root of 5 plus Mp, this is 3 times square root of 5. Okay, again. Tm is 3 over square root of 5 and Mp is 3 times square root of 5. So in total, Tp equals to 3 over square root of 5 plus 3 times square root of 5. So Tp equals to 3 over square root of 5. Here we multiplied 3 times square root of 5 by square root of 5 and then we divided by square root of 5 in order to overcome factor with this number. So square root of 5 times square root of 5 is 5 and 5 times 3 is 15. So in total the numerator of this expression we have 15 and we have to divide it by square root of 5. We will divide it by square root of 5. So in total we found out that Tb equals to 3 plus 15 over square root of 5. 3 plus 15 is 18. So in total the length of side Tp of square TSQP is equal to 18 over square root of 5 units in its length. This is side Tp, it is equal to 18 over square root of 5 units in its length. Our task is to find out the area of this ring shape. So what is the area of the ring shape? From the drawing it is very easy to see that the area of this ring shape in total equals to the area of the big square TSQP minus the area of this quadrilateral MBCP minus the area of this right small triangle TMB. But again, the area of this ring shape in total is equal to the area of the big square TSQP minus the area of quadrilateral MBCP minus the area of the small right triangle TMB. So what is the big square TSQP? This is square TSQP. You know that the area of any square equals to the length of one side squared. And therefore the area of this square TSQP will be equal to the length of side Tp squared. That is to say it is Tp squared. The area of the big square TSQP is equal to Tp squared minus the area of quadrilateral MBCP. According to what is given in the question, the area of this quadrilateral MBCP is equal to 27 squares in its size. So it is minus 27 minus the area of the small right triangle TMB. This is the small right triangle TMB. What is the area of this small right triangle TMB? Actually, you know that the area of any triangle equals to the base of the triangle times the height to the base over 2. Therefore, the area of this triangle TMB will be equal to the base TB times the height Tm over 2. And again, the area of the small right triangle TMB equals to the base TB times the height Tm over 2. So the area of the big square TSQP equals to Tp squared. Tp is 18 over square root of 5 and therefore Tp squared is 18 over square root of 5 squared. Minus 27 minus the base Tb is 6 over square root of 5. Tm is 3 over square root of 5 divided by 2. 18 over square root of 5 squared is equal to 18 squared, it is 324 over square root of 5 squared, it is 5. So in total, the area of the big square TSQP equals to 324 over 5 squared in its size. And here we have minus 27. And here we have this expression. In total, the value of this expression will be equal to 6 times 3 is 18. And here we have square root of 5 times square root of 5 is 5. And 5 times 2 is 10. So in total, the value of this expression is 18 over 10. So it is minus 18 over 10. Here we have 324 over 5 is 64.8, minus 27, and minus 18 over 10 is minus 1.8. 64.8 minus 1.8 is 63, minus 27. 63 minus 27 is 36. So in total, we found out that the area of the green shape equals to 36 square units in its size. The area of this green shape is equal to 36 square units in its size. So we finish with the first question. In the next step, I present to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. So, in the drawing, we have square ABCD. You know that AB equals to 10, therefore on the other side, AD, DC, and CB must be also equal to 10. In addition, inside this square ABCD, we have this quarter circle. The center of this big quarter circle is at point A. So point A is the center of the quarter circle, point B is the point of the quarter circle itself, therefore AB is the radius of the quarter circle, that is equal to 10. Likewise, AD is also the radius of the quarter circle, that is 10. AD is also one side of square ABCD, so, and AD is also the radius of the quarter circle, that is equal to 10. In addition, we have, this is the semicircle, inside the square we have this semicircle. BC is the diameter of the semicircle, that is equal to 10. We define the center of the semicircle, this point is point O. If the diameter BC of the semicircle equals to 10, it means that the radius must be equal to 10 over 2, that is 5. So the radius OB of the semicircle is 5, and the radius OC is also 5. In the next step, we define the intersection point between this big quarter circle and this semicircle. This point is point M. And we join points O and M together by straight line. Point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle, that is equal to 5. Likewise, we join points A and M together by straight line. Point A is the center of the quarter circle, point M is the point on the quarter circle itself, therefore AM is the radius of the quarter circle, that is equal to 10. What is the definition of line segment AM? Line segment AM is a tangent. That is to say, line segment AM is tangent to the semicircle at point M. Here we can implement rule 1, because according to rule 1, we have the radius OM of the semicircle that is equal to 5. The radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. Whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius AO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees according to rule 1. We know that all the angles inside the square are right angles. So in square ABCD, this is a right angle. In the next step, we join points A and O together by straight line. By joining points A and O, created those two right angles. This is the right angle ABO, and this is the right angle AMO. In the next step, we prove that those two right angles can go into each other according to side rule. So why those two right angles can go into each other? First of all, side OB of the right angle ABO is equal to side OM of the right angle AMO. They are both the radius of the semicircle that is equal to 5, and therefore they are equal to each other. And again, ABO equals to OM equals to 5. In addition, side AB of the right angle ABO is equal to side AM of the right angle AMO. They are both the radius of the quarter circle that is equal to 10, and therefore they are equal to each other. Repeat again. AB equals to AM equals to 10. And finally, AO is the common side that belongs to both triangles, so we can write down that AO equals to itself is the common side that belongs to both triangles. And again, AO equals to itself is the common side that belongs to both triangles. So if we found out that all the three angles of this big right triangle ABO corresponding equal to all the three angles, all the three sides of this triangle ABO corresponding equal to all the three sides of this triangle AOM, and therefore those two right triangles can go into each other according to side rule. And again, if we found out that in total that the right triangle ABO is congruent to the right triangle A1 according to side rule. In the next step, I copied the right triangle ABO in a new page and represented the Pythagoras theorem on this right triangle ABO. This is the right triangle ABO that I copied from the original drawing. In this right triangle ABO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so we leave it as it is, so it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus OB squared. OB is 5, therefore OB squared is 5 squared, that is 25. So in total, AO squared equals to 100 plus 25, that is 125. AO squared equals to 125. Here we substitute 125 by 25 times 5, and so we have AO squared equals to 25 times 5. Here we took out all this equation and find out that AO equals to the square root of 35. The square root of 25 is 5. So inside the root we left only with 5. So in total we should find out that AO equals to 5 times square root of 5 units in its length. This is not side AO. This equals to 5 times square root of 5 units in its length. We continue to focus on the right triangle ABO. On the right triangle ABO, sinus alpha equals to BO over AO. So again, in the right triangle ABO, sinus alpha equals to BO over AO. BO is 5, AO is 5 times square root of 5. So again, BO is 5 and AO is 5 times square root of 5. So sinus alpha equals to 5 over 5 times square root of 5. We have 5 in the numerator, 5 in the denominator, so 5 will get cancelled, and we left only with 1 over square root of 5. So in total we should find out that sinus alpha equals to 1 over square root of 5. Our task is to find out the value of angle alpha itself, the size of angle alpha. In order to find out the size of angle alpha, we'll operate the opposite function of sine, that is arc sine, on the result of sine alpha, that is 1 over square root of 5. In this way, we find out the value of angle alpha itself, the size of angle alpha. Repeat again, we'll operate the opposite function of sine, that is arc sine, on the result of sinus alpha, that is 1 over square root of 5. In this way, we find out the value of angle alpha itself. Actually, arc sine of 1 over square root of 5 is 26.565 degrees in its size. So in total, we should find out that the size of angle alpha equals to 26.565 degrees in its size. Therefore, 2 alpha must be equal to 2 times 26.565, that is 53.13 degrees in its size. Okay, this is angle MAB, that is equals to alpha plus alpha, that is 2 alpha. Therefore, we just now found out that angle MAB is equals to 2 alpha, it is equals to 53.13 degrees in its size. We will continue to focus on this right triangle ABO. In the right triangle ABO, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle ABO? We have alpha plus beta plus 90 degrees. In total, it must be equal to 180 degrees, according to the rule that I mentioned. So in the right triangle ABO, alpha plus beta plus 90 degrees, in total it must be equal to 180 degrees. Here we subtracted 90 degrees from this equation, and I found out that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtracted alpha from this equation, and I found out that beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha. Alpha equals to 26.565, and therefore beta equals to 90 degrees minus 26.56 degrees, and 90 degrees minus 26.565 degrees, it is equal to 63.345 degrees. So in total, we should find out that angle beta equals to 63.435 degrees in size. And therefore, 2 beta must be equal to 2 times 63.435 435, that is 126.87 degrees in size. Okay. This is the big angle MOB. MOB equals to beta plus beta, that is 2 beta, and we just now found out that 2 beta equals to 126.87 degrees in size. So angle MOB is equal to 126.87 degrees in size. Yeah. Angle MOB, that is 2 beta equals to 126.87 degrees in size. Our test is to find out the area of this green shape. In order to find out the area of the green shape, we join points M and B together by straight line. By joining points M and B, we divided this green shape into two parts. This is the first part and this is the second part. The first part is a segment, so we'll define the upper segment, this upper segment, a segment VUM, and we define the lower segment, this is the lower segment, a segment MLB. So we find out the area of each segment separately, and then we'll add the two areas together, and this will be the area of this green shape, that is the area that we are looking for in this question. Very simple. So in order to find out the area of the lower segment BLM, I copied sector A and B in an equation, and analyze this sector A and B. This is sector A and B that I copied from the original domain. What is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. And again, the green shape is sector A or B, and a sector A or B is a portion of this circle enclosed by two radii and the arc AB between them. It's like a slice of a pizza. The two radii are AO and BO are the two radii that are defined also as the legs of the sector. So the area of this sector AOB equals to pi r squared, that is the area of this circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. And again, a sector is a portion of a circle enclosed by two radii and the arc AB between them, and the area of a sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. Use the new formula in order to find out the area of this sector A and B. According to the formula that I presented to you, the area of this sector M and B will be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 55.13 degrees in its size, over 360 degrees. R AB equals to AM, the above the radii of the 42nd is equal to 10. So R equals to 10, and therefore R squared is 10 squared, that is 100, so pi R squared is 100 pi, times the angle between the legs of the sector. This is the angle between the legs of the sector, this actually equals to 53.13 degrees in its size. So the angle between the legs of the sector is 53.13 degrees in its size, divided by 360 degrees. So R is 10, therefore R squared is 10 squared, that is 100, so pi R squared is 100 pi, times the angle between the legs of the sector, that is 53.13 degrees, over 360 degrees. In total, the value of this expression, 100 pi times 53.13 degrees over 360 degrees, in total is equal to 46.3646 square units in size. So if you found out that the area of this sector ABM is equal to 46.3646 square units in size. Our task is to find out the area of this lower segment MLB. This is the lower segment MLB that we have to find out the area of it. From the domain, it is very easy to say that the area of this segment BLM will be equal to the area of sector A and B minus the area of triangle A and B. It is very easy to see that if you remove from this sector A and B this triangle A and B, we get segment MLB. And therefore, the area of the lower segment MLB will be equal to the area of sector A and B minus the area of triangle A and B. We already found out that the area of sector A and B equals to 46.3646 square units in size minus the area of this triangle A and B. In order to find out the area of this triangle A and B, I presented to you a new formula that will help us to find out the area of any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. The area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. And again, the area of this triangle ABC that could be any triangle equals to the multiplication of two sides by each other, that is to say AB times AC times sinus the angle between those two sides, that is theta, so it is sinus theta over 2. We use the new formula in order to find out the area of this triangle ABM. According to the new formula, the area of this triangle ABM will be equal to the multiplication of two sides by each other, that is to say it is AB times AM times sinus the angle between those two sides, that is 53.13. So it is sinus 53.13 degrees divided by 2. So in total, the area of this triangle ABM equals to AB times AM times sinus 1.3 degrees over 2. AB is 10, AM is 10, so AB times AM is 10 times 10. Sinus 53.13 degrees is equal to 0.8 divided by 2. 10 times 10 is 100, so it is 100 times 0.8 divided by 2. 100 over 2 is 50, and 50 times 0.8 is 40. So in total, we should find out that the area of this triangle ABM is equal to 40 square units in its size. And therefore, the area of the lower segment BLM will be equal to the area of sector ABM, that is equal to 46.3646 square units in size, minus the area of this triangle ABM, that is equal to 40 square units in size. 46.3646 minus 40 is equal to 6.3646 square units in size. So I should find out that the area of this lower segment BLM is equal to the area of the lower segment BLM is equal to 6.3646 square units in size. The next step, we found out the area of this upper segment BUM. We found out the area of this upper segment BUM. In order to find out the area of this upper segment BUM, I copied sector BOM in a new page and realize this sector BOM. This is sector BOM that I copied from the original drawing. The angle between the legs of the sector is 126.87 degrees in its size. The two legs OM and OB, the two legs of the sector OM and OB, they're both the radii of the semicircle, that equals to 5. So OM equals to 5, or OM equals to 5, and OB also equals to 5. According to the formula that I presented to you a couple of minutes ago, the area of the sector OBM, the area of the sector OBM will be equal to pi r squared, that is the area of the circle that contains the sector. R is 5, times the angle between the legs of the sector, that is 126.87 degrees in its size, over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi, times 126.87 degrees over 360 degrees. In total, the value of this expression, 25 pi plus 25 pi times 126.87 degrees over 360 degrees, in total it is equal to 27.678 square units in size. Okay, again, we found out actually that the area of this sector BOM is equal to 27.678 square units in size. Our test is to find out the area of this upper segment BUM. We have to find out the area of this upper segment BUM. It is very easy to say from the drawing that if you remove from this sector BOM this triangle BOM, we get exactly segment, the upper segment VOM. So therefore, the area of the upper segment VOM will be equal to the area of the big sector BOM minus the area of triangle BOM. Repeat again, if you remove this triangle from sector BOM, you get exactly segment BOM. Therefore, the area of this segment BOM, the upper segment BOM equals to the area of sector BOM minus the area of triangle BOM. We already found out that the area of this sector BOM equals to 27.678 square meters in size minus the area of this triangle BOM. Use the new formula in order to find out the area of this triangle BOM. According to the new formula, the area of triangle BOM will be equal to BO times OM, that is the multiplication of two sides by each other, times sinus angle between those two sides, that is 126.87 degrees, that is sinus 126.87 degrees divided by 2. BO is 5, this is the radius of the semicircle. OM is also 5, times sinus 126.87 degrees. Sinus 126.87 degrees is equal to 0.8 divided by 2. So in total, the area of this triangle BOM is equal to 5 times 5 times 0.8 over 2. 5 times 5 is 25, and 25 over 2 is 12.5. 12.5 times 0.8 is 10. So in total, we should know that the area of this triangle BOM is equal to 10 square meters in size. And therefore, in total, the area of this segment, the upper segment BOM, will be equal to the area of sector BOM, that is 27.67 square meters in size, minus the area of this triangle BOM, that is equal to 10 square meters in size. 27.678 minus 10 is 17.678 square meters in size. So we found out that the area of this upper segment BOM is equal to 17.678 square meters in size. This is the upper segment BOM. We just found out that the area of this upper segment BOM is equal to 17.678 square meters in size. Our test is to find out the area of this green shape. It is very clear from the drawing that the area of this green shape is equal to the area of the upper segment BOM plus the area of the lower segment BLM. And again, the area of the green shape, this is the green shape that is going from the original drawing. The area of this green shape equals to the area of the upper segment BOM, that is 17.678 square meters in size, plus the area of the lower segment BLM, that is equal to 6.3646 square meters in size. And 17.678 plus 6.3646, in total it is equal to 24.0426 square meters in size. So in total we should find out that the area of the green shape, the area of this green shape, that is the area that we are looking for in this question. In total it is equal to 24.0426 square meters in its size. Okay, thank you very much.